Yes. Alright, let's start with some more real-time operating systems. So we talked about pulled loop systems and intro-driven systems just now, last lecture. And we're going to talk a little bit more about multitasking in foreground-background systems. So a quick recap. So when we talk about pulled loops, we effectively just have an infinite while loop, just one task in which you check conditions, just a flag that is being set. For example, a ready flag when you use the UART, that then tells you if that ready flag is set, that the string has appeared and has been collected, and so you're ready to interpret that particular string. Now, if you have just one single while loop, one task effectively may be checking multiple conditions, you do not really need inter-task communication. So the whole idea is really that we like to abstract away a little bit. What we want to do is we want to see effectively multiple programs, if you will, that all are concurrently running on your MCU. So say you have one infinite while loop that is doing some task at some regular moments. That's at least what you would like to do. You have another infinite while loop that has maybe some other tasks that are being computed and so forth. Now clearly you only have a single program that is sequentially being executed, but from a designer's perspective it's kind of nice if you could model it like that. So if you could write, say, a task that will be called on and on and on according to some kind of policy that you have set, and another task that will be called on and on and on. And you would like to program these maybe as being tasks that are all the time being executed in some infinite while loop. So what the real-time operating system can do for you is that you can effectively make that abstraction. You could essentially create a process, if you will, or a task with certain parameter settings, with the idea that during an infinite loop that task will be called. And you do the same for another task, and the same yet for a third task, and so forth. Now if you take that abstraction, then your real-time operating system needs to allow you to talk between tasks, because you want to send messages from one task to the other and back. So that's why you would like to have inter-task communication for a more complex system that is not just pulled loops, which is essentially just one main task, like one infinite while loop, the way we have been programming it so far. So in such a simple mechanism, then the pulled loop actually reduces to very simple kernel effectively, no inter-task communication, and so on. Now, we would like to abstract away from that, as I said, and allow us to have more independent tasks. So we will come to that throughout this lecture. Now, the other thing that we talked about was an intro-driven system, and we closed off with this particular example. And here we see that based on events that actually happen, your MCU will be interrupted, and you should then execute a certain type of code. Now, we've been talking about interrupt service routines. Those are specific routines related to the different interrupts that your MCU can handle, like external interrupt and so forth and so forth. But the point is that those hardware events that call those interrupt service routines, they may actually come from actual events like these. For example, your aircraft that we're talking about needs to be, there's some threat that is being recognized somehow, and you sound a cockpit alarm, or your low altitude indicator triggers that, oops, you're way too low, you need to fly up. So those kinds of triggers, those kinds of detectors, if you will, they may create like that external interrupt that then will lead to an interrupt service routine call in your MCU. Question?
Could you make multiple external interrupts at the same time then? Like say you're flying at low altitude And then also,
Well, MCU has only two external interrupt pins, so those can be used for external interrupts. The question is, can you multiplex those pins for handling multiple types of external interrupts? Yes, you could, because once the external interrupt actually is triggered, then maybe your interrupt service routine that is called will then look maybe for some additional signal that is being transmitted, so that you can figure out how to handle this particular interrupt, because it may come from a bunch of various reasons. But yeah, there's so many options really, but yes. And so what we want to do is, we want to think, so I'd like to make that distinction once more, right? So when you have been programming so far, right, you have been creating several procedures. Each procedure is like a function that you execute in its whole, and then you go back to the main program, and then you go and you may call yet another function. Even, for example, computing design, for example, is a library call, is a function on its own that is being called, and then you come back. So you have functions, and then you have these tasks. So far I've been talking about tasks in a way that we have this one single infinite while loop, and we have within that infinite while loop, in some kind of round-robin fashion, we check whether, say, the string has arrived from the UART. Then we check whether we should be ready to write something on the LCD screen. And then we may check a third component which says maybe some information has come in through a button push or something like that. So within that single while loop, in this task-based programming style that we have been developing so far, we see effectively these several options that we check in a round-robin fashion. And those different if statements with the procedures that we will call if the condition is met, those procedures we have called tasks up to this point in time. But now I'd like to abstract away a little bit. So the idea is that we have an infinite while loop, just one task, and I always check, for example, in a poll loop system, whether the ready flag is there, and I do that forever. And I have a separate infinite while loop that is doing that for, say, my print to the LCD screen, which I want to only do, say, every 1 second or something like that. I'm just saying something, so you need to schedule that in a different way. Now, clearly you cannot program in your main program, say, 5 different infinite while loops. You don't do that. But the real-time operating system makes you think you do. That's the point. So the idea is that you can literally with a task create a process like something that you have in mind, say checking for the ready flag and then your string has arrived, and you can create multiple of those processes, and to you it seems like those are these infinite while loops that will always be running, but the operating system is going to context switch in and out. That's how we call that, the different computational threads, like the different while loops that you want, the different processes that you want to execute all at the same time. So your real-time operating system is now in charge of that scheduling of the resources, in our case the computational resources. And how does it do this? Well, it can employ several strategies. And in effect, when you create a process or a task thread, then you are also in charge of using the real-time operating system's vocabulary to indicate with some parameters what kind of priority you give that particular task, and so forth. Now, among all these different task threads, you would like to have some communication. So that is important too. So you would like to be able to pass information computed in one thread to another thread. Say, I received a string in one task and I like to pass it on to, once I have interpreted, I like to pass on the response message to the LCD screen printing task, and so forth. So, when you now think about these tasks as these individual processes, then it seems to this particular task, and also to the application designer who creates it, that that task owns the processor completely. It's like none of the other processes actually exist to it in a way. It sees its own variables, and it may be interrupted because of some hardware events or whatever it is. So you may actually really have like an interrupt service routine call may happen, or the real-time operating system may interrupt it because it wants to context switch it out and bring something else in. So the point though is that from the point of view of, say, this get string task that we just talked about over the UART, right, that particular task is some small modular code module that is totally oblivious to whatever happens outside of it. It doesn't matter. It has its own global variables. It has its own state. And the real-time operating system may context switch that out and start executing another such module. And how do you get a whole program? Well, the whole key idea is that all these modules communicate with one another and exchange information. Now, why do we even like to do it like this? It turns out that if you have this modularized way of designing, you have a much better overview of what is actually happening in your code. So a small module you can understand. You write the specification for it, like, well, this module will output this particular stuff under these and these conditions, and will do this under these and these conditions. So there it is. It's a spec. You write that particular task as such, and that will become one of your computational threads in the real-time operating when the real-time operating system is managing it. And now you have all these other modules in a similar way, and now you need to combine all those specifications together, because in practice, you know, you would work with fairly complex systems in the end, when you work in a team with multiple people and so forth. Then someone can truly be responsible for one task, and yet another task, and yet another task. A priori you have defined the specs. You may even need to change the specs a little bit once you try to combine them. You will notice that maybe it doesn't completely work out the way you had hoped for. So you may need to fine-tune, especially when it comes to timing. In a real-time, you know, embedded systems world, you know, you need to adhere to certain timing constraints. So you may need to play with that as well. So you converge and you get the specs for the individual task in a good form, and then the whole system will start to work for you by this inter-messaging between those tasks. But from a single task perspective now, it really sees, it thinks it has the whole processor for itself. It simply does not realize that it will be put to sleep at some point, and it will wake up later on, and while it was sleeping, some other task actually owned the processor and got control over all the resources. Alright, so that is sort of the broad picture. And so if you're thinking about this particular example, then you can see there's a whole bunch happening. So first, let's go through this a little bit. So say we have this airplane environment, and we have some navigation system software. So suppose we have navigation sensor tasks. So we have a bunch of sensors, and those sensors, they will create some data. The data is being stored in some shared memory. So for example, the sensors may measure, say, the temperature of a certain area of the airplane, you name it, and what it records is being put in some shared memory. It can also, serve as inputs to other components, that's fine, but the whole point is also that the shared memory, or all that is being collected by those sensors, is being parsed in a way by a navigation filter. And there are different possibilities for this. And in order to actually read the memory, you have a memory read operation, you have a memory write operation to put things into the memory. So you have some shared memory that is, accessed by all these processes at the same time. And when we're talking about the memory, effectively, you can think of it as being, a mailbox. So as a mailbox is simply the circular buffer that we've been talking about, like an array with a pointer, and you just override the oldest value with the most recently sensed value. And so you keep a history, but it's like a buffer, and you keep on overriding. And that buffer is being accessed by these other processes. So the navigation sensor task retrieves data from sensors. Each task can only see its own data. A clock-driven scheduler, which is the operating system, right, drives the tasks at various frequencies to write sensor data to the shared memory. And then the navigation filter over here retrieves the data at scheduled intervals. That is sort of how you want to look at it. Now, how can the scheduler work? Well, it needs certainly a real-time clock, so say a timer 0 or a timer 1, right? So with that software clock, the scheduler can now actually perform the right order of task computations. Alright, so let's talk about context switching, because apparently what we need to do is we want to be able to take one task out and bring another one in. So what do we need to do? Well, when the CPU switches from one task to running another, that is what we call a context switch, then what do you need to do? You need to save the minimum needed to restore the interrupted process, because the whole idea is that the process, the task, will actually be interrupted, so it sees all its own variables and so forth, is put to sleep, and when it wakes up, it should just continue computation as if no interrupt had happened at all. That is important. So we need to store the contents of registers. You've already seen that when we talked about interrupt service routines, right? We do that too. The contents of the program counter, the contents of the coprocessor registers, if those exist, memory page registers, all kinds of stuff, memory net I/O, special variables, blah blah. And since a context switch is so crucial, you do not want that to be interrupted, really. So during such a switch, the interrupts are often disabled. Now that's dangerous, because a context switch, if it takes too long, you miss out on hardware events, and you can imagine how terrible that potentially could be. So in real-time systems, they require these context switches to be performed in very small times. Like, that's the whole goal, minimal times for context switches. So that defines effectively how good your real-time operating system will be. It's a very important requirement to make those context switches blazingly fast. Alright, so now that we've given the bigger picture and we see this context switching, then obviously, when do we do the context switching? How do we do this multitasking? So what kind of strategies could we employ? So here are a couple: cyclic executive systems, round-robin systems, and preemptive priority schemes. So we'll talk about each of those to give you an idea of what's going on here. So a cyclic executive system is a very simple one. Effectively, here you see a bunch of tasks, processes, and they are just statically ordered threads, like you do the first and the next and so forth. You first do this one, you wait till it's completed, then you do that one, you wait till that one is completed, and this, and you go back, you again do data in, and so forth. So you do all these tasks, you call them, and you just wait. So it's easy to implement. It's used extensively in complex safety critical systems, actually, because there's some clear understanding of the timing deadlines that you have here. The cons are it's not efficient in the overall usage of the CPU processing, actually, and does not provide optimal response time. Like maybe I would like to do some navigation here as well, simply because a very important, maybe anomalous input data from the sensors came in that would require you to respond fast. But now you have to wait till your turn comes. So, what about other possibilities? Well, the round-robin systems, here several processes are executed sequentially to completion, but it's often in combination with what we're doing here, so one task after another. But now the difference is that each task is assigned a fixed time slice. So I say, you got like 1 millisecond right now. I'll give that to you. But hey, I'll kick you out, even if you're not finished. I'll kick you out, and context switch something else in, and then it's your turn again. According to my schedule, I'll bring you back, and you can continue as if nothing ever had happened before. But that's what I do. So now you can use a fixed rate clock, which initiates an interrupt at a rate corresponding to that particular time slice that you have in mind. So maybe you say 1 millisecond for task 1, then you interrupt it, context switch, you step to task 2, task 3, task 1, task 2, and so on. So 1 millisecond, 1 millisecond, 1 millisecond, and so forth. Very simple time multiplexing of the computational resource. This is actually similar to our task-based programming without the fixed time slices per task, right? We also say, okay, if you look through our while loop, so think of our while loop as being a very simple real-time operating system, right? With a scheduling mechanism that says, okay, I will first look whether the cat string is ready, and if so, let's get it. Next, that was task 1. Then task 2, print on the LCD screen if I'm ready for that. Next, look what the button push has given me or what. And so I go back, I keep on going in a round-robin fashion. The difference is that we do not really say, okay, the interpretation of what we received over the U-word is taking a little bit too long, so let's interrupt it, do a context switch, and start off with task 2 already, and then later on continue with task 1. That's not what we do. So, but you can see that this round-robin style of thinking is what we did in our task-based programming.
I have a question.
Yeah.
So overall, is this more efficient to do it this way compared to holding up on one task? I guess it depends on the program.
Well, we will see at the end some examples, and it really depends on what you want, how you will schedule. And different specifications really will want you to do in one case a certain type of methodology, in another case another type of methodology. So it's all over the place. And actually, in general, what you want to do is to mix. A good real-time operating system allows you to do a mix of different strategies all at the same time.
So let's say task 2 and 3 are dependent on the output of task 1. So then we could do it'll just be finish task 1, but then implement the stop for tasks 2 and 3 afterwards.
Yeah, so now you're talking more about a finite state machine. You need to effectively wait for task 1 to finish in order to get task 2 going. So the question is then, suppose task 2 and 3 wait for that output of task 1, and then you may have a more complex scheduling system that decides whether we would then do task 2 first or task 3 first, or but then I may be in danger, because if I do task 3 first and so forth, and we'll come to an example in a moment, you can get strange artifacts as well. So there's all kinds of interesting questions one can ask about how to schedule stuff. That's why there's so many different schemes and possible solutions. There's all kinds of different ways to go for it, each with their own pros and cons. And it's up to you as an application designer, what do you want? So let's go into preemptive priority systems, which will show you some of their complexity. So say, what we can do in this particular mechanism is that we assign priorities to tasks. So a higher priority task can preempt a lower priority task if it interrupts a low priority task. So, say in this particular setting, task 2 has a higher priority than task 1. Hey, it's ready to go. For example, a certain interrupt has been generated, and so you have a mix of, say, a round-robin way of looking at it together with an interrupt-driven type of signaling that says task 2 should go. And why should it go? Because there's a higher priority than task 1. So I'm not going to finish task 1, I'm going to context switch that out and start task 2. But wait, another task 3 is now coming in and says, I need to get the resources. And the only reason why task 3 starts here is because it has a higher priority than task 2. And then later on when it's finished, task 2 can finish, and then task 1 can finish. So the priorities here are that are assigned to each interrupt, right? That tells the real-time operating system that a certain task needs to get going, are actually based upon the urgency of the task associated with the interrupt. Again, the application designer is in charge. He needs to set those priorities, but they do not necessarily need to be fixed. They can be dynamic. So the actual program can change those priorities, and even the real-time operating system, as we will see in a moment, can temporarily change the priorities in order to eliminate certain artifacts. So here we have, for example, a round-robin system with a preemptive scheduling of 3 tasks. So you start, for example, this came in, and then this, it preemptively, kicked this one out to start this one, and so forth, and we go forward. So here we have the example of the aircraft navigation system. High priority could be a task that checks the accelerometer data every 5 milliseconds. A medium priority could be one that collects geodata and compensates this data and accelerometer data every 40 milliseconds. A low priority could be one to display updates, do some built-in testing, and so forth. So, what are problems with this multitasking approach? Well, high priority tasks have high priority, so they kick everybody else out. So that means that they can get too much control maybe over the resources, and the other tasks simply do not have time to finish or to do good work. So you starve low priority tasks. Low priority tasks, on the other hand, they may share a resource with a high priority task, and this low priority task may actually use that resource, but since it is not finished, the high priority task cannot yet start, because that particular piece of memory or whatever it is not yet available for the high priority task. So that can lead to a problem. And the next slide will show you how that works. So the real-time operating system needs to deal with these types of problems. And one thing is that we can use rate monotonic systems, where higher execution frequency is related to a higher priority, and that means that we can sort of eliminate that very first bullet negative or that problem that could occur. And to combat the next one, we'll talk about priority inheritance. So let's first explain the problem. Say task A and task C share a resource, task A has high priority and task C has low priority. But task A is blocked when task C runs, because they share a resource. So what does that mean? Effectively, this assigns to A C's priority.